Hi, welcome to Team 21 Project 2 presentation. As the climate change problem worsens, solar energy has become a popular source of energy due to its sustainability. However, it can be harnessed at every hour of the day. So our task was to create an optimized model of a hydro pump storage system. In this system, the solar energy pumps water into a reservoir, and this energy is stored as potential energy, and when needed, it's transformed into electricity by the turbine.
Okay, so the team's next task first task in the beginning of the project was establishing project management standards. And the first thing we did was create a needs finding chart. So our customer needs, we had about 5 of them. They were high model sophistication, cost efficiency. This included building and operation costs. Model/study must be well defined, uses energy efficiently, and is environmentally friendly. And overall, we kind of labeled that the environmentally friendly, energy efficiency, and cost efficiency were the most important. But overall, this is our needs finding chart. And our technical needs for each of those were for high model sophistication. We had number of pumped hydro storage system components that were described in the model. This would be presented in the code. Cost efficiency, the technical need would be total cost here. The model/study must be able to find. The technical need was amount of data from the model/code for each storage system component. Use energy efficiently. Our technical need was wasted energy, and this is measured in megawatt hours. And our last customer need, which is environmentally friendly, the technical need was amount of land taken up from system. And overall, our goal was to optimize the customer needs while maintaining what we believed would be best for the system, and that was established through code. And the group's next task was to create a work breakdown structure. And the first level of this work breakdown structure included bend/pipe management, cost management, location selection, material selection, and energy management. Some subcategories we had under bend/pipe management were the length, the friction coefficient, the bend angle, how steep the angle is, and the diameter of the pipes. For cost management, some subcategories were total cost, and this was just building and operation. Location selection, we wanted to optimize being environmentally friendly, which was a customer need, versus overall optimization of the land, using the heights available and the land that's actually usable. And overall, we ended up getting selection, the area 3 as our selection. And we also wanted to understand the cultural concerns of this. So to understand that, we wanted to minimize the land destroyed and maximize the land recovery. Our next category was material selection. This would be established through a set of code. And energy management, some subcategories were flow rate up and down. And megawatt hours is what this would be measured in. And this is it for our project management.
After our project management step, we went into modeling about which factors we thought were the most detrimental and felt like had the biggest impact on the overall efficiency of our hydro pump system. And the 3 that we came up with was pipe friction, pipe bends, and foreign objects. In pipe friction, we model how much energy would be lost using the Darcy-Weisbach equation. In the pipe bends, it was a similar equation as far as pipe friction, where a coefficient of a pipe bend factor, which would increase as the angle of the pipe increase as well, and foreign objects, which we modeled by similar how we did turbine efficiency loss, where a coefficient was used that was correlated with how much coverage was done by a foreign object. And we came up with our third factor by doing some research as far as what were some prevalent issues with hydro systems that are already in place. And one of them was an algae bloom in several reservoirs that clogged the pipes, which we estimated would slow down the flow rate due to it covering part of the pipe. And since it could cover up to 40% of the pipe area, going down, it could affect the flow rate significantly and reduce the efficiency of the overall system, making the energy needed to input into the system to be increased. And the fourth one, which was a known factor as far as efficiency, was turbine turbine loss, as also coefficient for pump loss, which is due to all machines are not perfectly made. So we had to take into those into account when modeling, when creating our final model, and that's implemented in our code to find how much energy needs to be inputted to get the constraints that we made for ourselves in our needs finding and work breakdown structure.
Okay, so now onto the code. So as you can see, we have all of our inputs up here at the top, and right here we manually typed out all of the data that we were given in the cost sheet. And the idea here was so we could automate the process of plugging in values so we could optimize it a little easier. We later found out that when we tried to optimize automatically, that there was so many combinations that the code would run for an extremely long amount of time. And even after reducing the number of variables that were optimized, the output file that we wrote to was about 14 million lines long. So it was going to take forever to sort through all that data. But what this did let us do was figure out the trends and how we can manually optimize the variables ourselves. So for example, the friction factor is obviously just going to make it more efficient as the friction factor gets lower. So that was just an unnecessary extra variable that we were trying to optimize. Down here is just calculating the losses, and then eventually it adds the losses and then calculates the energy in. And then another section is the cost section, where it automatically calculates the cost of each one, which is just as important as the energy. And to find the cost, it would take these values and use the index function to figure out exactly what number in these lists it needed to multiply by. And most of these numbers in these lists are some kind of cost associated with that category. So I already have typed in all of the variables and numbers that we optimized for our site 3. So I'm just going to run that. Yeah. So, okay, so the total cost was about $472,000, and our energy required in was 120.8 megawatt hours. That's an extremely small energy in, considering that the energy out is 120 megawatt hours, and we credit our low flow rates and our large pipe diameters for that. When we automated the process of calculating our outputs, it showed us that the flow rate could be a lot smaller, and it could range from 1 to 500, but we found that you want to minimize the flow rate as much as possible. So on that specific one, we ended up having the flow rate at 19 cubic meters per second on the way down. And that was just to make sure that we could create that 120 megawatt hours of energy in the allotted 12 hours of time. And then to minimize energy loss due to pipe friction and other factors, we wanted to keep the flow rate as low as possible on the way up as well. So that was about 5 cubic meters per second. So this all led us to choose the third zone, and we think we optimized pretty well. That was our lowest cost and our lowest energy. It was pretty close to another one on cost, but the energy savings was significant enough for us to go ahead and pick zone 3. We think it had a minimal impact on the environment, and it was a sustainable design. So that was our project 2 for Team 21. Thank you for listening.